So I just bumped into an old student of mine. I taught him earth space science, and in that class we were learning about maps and stuff like that, and compasses, and talking about how to orientate ourselves with the compasses anyways. So I just remember I asked him last year, I said, you know, if you were facing north and your back was due south, what would be on your left hand? And I remember he told me 5 fingers. Touche. He got me. He got if whatever. What are you gonna do? What are you gonna do, huh? Anyways, this is the 14th topic of chemistry, not earth space science, and we're talking about acids and bases. So let's get rolling here. Why don't you stop the video right now and just make a guess on what the following 5 substances are. Are they acids or bases? So just a little prior knowledge. Just pause the video and make a guess. And hopefully you did that. And let's see how you did. Vinegar, and it doesn't matter if you got them right or wrong, but vinegar is an acid. Baking soda is a base. Soap is a base. Orange juice is an acid. And believe it or not, some people miss this last one, antacid tablets. It's a base. And a lot of times people say, well, it's an acid because it says acid. But also ant means anti, not. So this literally says not an acid. It's a base. But that's just a little prior knowledge. So you may have already some knowledge about acids and bases before this lesson already started. That's all I'm trying to...
I love vocabulary.
That's all I'm trying to talk to you about. So, definitions. The first definition is we're going to define an acid, and we'll define a base. And an acid is a substance that donates hydrogen ions. And that's this guy here. To form hydronium ions, which is H3O positive when dissolved in water, because water is H2O, and if you add an H positive to H2O, then it's H3O positive, because we added the charge and the hydrogen. So when hydrogen ions are in solution, it makes hydronium, and that's what an acid is. Bases are substances that either contain hydroxide ions that are released into the solution or reacts with water to form hydroxide ions. So hydroxide is OH negative, and we remember, hopefully you remember that from our polyatomic ions list. It's a very important polyatomic ion because it's really a very obvious indicator that you're dealing with a base when you see hydroxide. So here's an example of an acid. We have HCl and water. So we have HCl reacting with water, and when HCl reacts with water, the hydrogen from the hydrogen chloride bonds with the water, making it hydronium and chloride. Now, a little nomenclature about naming of acids. So HCl would be referred to as hydrochloric acid. When you just have a single non-polyatomic acid, so it's just chlorine, it's not nitrate or something like that, you take off the end of the word, so instead of chlorine, we call it chloric, and we say hydro, and then you end it with acid. So it's hydrochloric acid. That's if it's just a single. If it's polyatomic, you don't have to say, actually don't, not that you don't have to, but you don't say the hydro. You just say, so if it's nitrate, you would say nitric acid. Okay, so examples of acids. This is an example of an acid reaction. And some examples of acids that you are familiar with in foods. We tend to eat foods being acids or bases. We tend to eat things that are acids. So some acids includes pickles, vinegar, and oranges. These are foods that are acidic. And a little talk about why do we eat more things that are acidic than basic. Well, this acid right here, hydrochloric acid, is the acid that's in your stomach. That's stomach acid. And acids and bases neutralize each other. So if we were to eat foods that were basic, that would start neutralizing the stomach acid. When you eat, you chew up your food, and then it goes into your stomach, and then it chemically breaks down your food more. You need that acid in there. So if you were eating food that was constantly neutralizing your stomach acid, you wouldn't be able to digest your food. You wouldn't be able to break it down. So it makes sense that instinctively, taste-wise, we are not attracted to things that are basic. We're attracted to things that are acidic because this complements our stomach acid. All right, bases. Here's an example of a base, sodium hydroxide. And a little note about naming things. This is sodium hydroxide, and you don't have to say anything different about it becoming a base. And acids, we have a different name. Remember, we put ic acid or hydroic acid, hydrochloric acid or hydrobromic acid, hydrofluoric acid. Yeah, anyways. So sodium hydroxide in water will produce, the hydroxide will break off, and then you will create sodium ions and hydroxide ions. The presence of the hydroxide ion is what makes this a base. Notice I just said in water, that's what this happens. If you have an equation where you have a reactant and a product that are both the same, it's like a fraction. If you get the same value on both the reactant and product side, or numerator and denominator, you can cancel them out. So we could say sodium hydroxide solid will become sodium ion aqueous and hydroxide ion aqueous, and we could cancel these two guys out here. But for definition purposes, I'm telling you that when you put it in water, it makes that acid. Examples of things that you deal with that are bases include soap, baking soda, and antacid tablets. Sometimes we eat that acid, and our stomach acids are getting a little bit too high, and it's getting beyond our stomach, which can protect us. Your stomach has a lining that protects you from those acids, and it gets up into your esophagus, and you don't have that protection. You feel it's actually that acid is burning you, and that's what we call heartburn. And so sometimes when you're feeling too much of that stomach acid, you might take something, antacid tablets, like here's Rolaids or Tums or something like that, and it's literally a base that's, it's a base with a buffer in it that's neutralizing that acid somewhat to give you some relief when that acid's burning yourself. So sometimes we take bases, but normally we don't like that. I know my parents' generation, but it didn't happen to me. But I remember my parents saying that, if they said a curse word, their parents would put soap in their mouth, and that's a base. And we don't like basic stuff. It's just, yeah, well, don't talk. Dirty mouth, so we'll clean it. All right, how do we measure the concentration? Well, we measure it in something called pH. pH is the potential hydrogen. Some of my students asked what that was, and I drew a blank in class, but I'll tell you right now, it stands for potential hydrogen. So the potential hydrogen is for your hydronium concentration, but we can also have a pOH, which would be measuring our potential hydroxide. So you can have a pH or pOHs. Regardless, in pH's example, it's the measure of the hydronium ion concentration in solution. If it was pOH, it would be the measure of the hydroxide ion in solution. The pH scale ranges from 0 to 15 typically, but I'm going to tell you a little bit about that scale in a moment, that it's not quite. But if you guys recall from equilibrium, we talked about kW. kW is 10 to the negative 14th. If you take the negative log of that, that's 14. And that's why we come up with a scale of 14. If you have equal parts of hydrogen and hydroxide, half of 14 is 7. So that's where you get that neutral area here. So the scale, those hydrogen and the hydroxide, I'm just going back to equilibrium where we talked about that, the hydrogen pH and the pOH of hydroxide will always add up to 14. So that's why we talk about the scale being 14. However, if your pH was -1, then your pOH would have to be 15. So because 15. So if it was 15 plus -1, that would still add up to 14. All right, our scale goes like this, and like I was saying here, neutral is 7. That means you have equal parts hydronium and hydroxide in solution. If it's less than 7, it's becoming acidic. If it's greater than 7, it's basic. And sometimes you hear things that are basic, we call it alkaline. You have the alkaline earth metals. If you put those metals in water, it starts reacting with the water and turning the water basic. So because those metals make water basic, they're called the alkaline earth metals. Alkaline metals do the same thing too. That's the base of why alkaline metals and alkaline earth metals are called the way they are, because they make water basic. They turn water into a hydroxide, part of the water at least. So let's analyze what pH actually means. Which is more acidic and by how much? Coffee has a pH of 5 and apple juice has a pH of 3. Hopefully right now you can understand that apple juice would be more acidic, but by how much? Well, we got to analyze what pH is right now. So 1 unit of pH is a factor of 10 hydronium ions. So it's a factor of 10. So if I was to say pH of 5 to pH of 4, let's put a 4 in between here, that would mean from 5 to 4, 4 has 10 times more hydronium ions than 5 does. And from 4 to 3, 3 has 10 times more hydronium ions than 4 does. So to go from 5 to 4 and then 4 to 3, it's actually 100 times more acidic. There's 100 times more hydronium ions in a pH of 4 than a pH of 5, because each shift is a magnitude of 10. And it's not, you're not adding them, they're multiplying them. So it's not 10 plus 10, it's not 20. That's a common mistake students make. They'll say that this is a strength 20 times stronger. It's 10 times 10, it's 100. My advice to you when you're doing this stuff is when you look at this, you see there's a difference of 2, add 2 zeros, or 10 to the second. And that's easier than, don't put a 2 in front, add 2 zeros. That's the easiest way when you talk about strengths in pH. Here's some common household things that you hopefully have some association with, and you can kind of take a look at the acidity of these different things. So human blood is actually slightly basic. Rainwater is acidic. Wine is more acidic, it's 4.0, and lemon juice is 2.0. This is even more acidic. So as we move this direction, we get more and more acidic. So the most acidic thing on this list is lemon juice, or lemons. And then we go to baking soda, detergent, and bleach. Bleach is much more acidic too. And you notice that bleach, if you put that on your clothes, it'll take the color out of your clothes. So being very basic, makes chemical reactions with different things, in particular the color molecules. But so will lemon juice. Lemon juice will take the color out of things too. So as you go to those extremes, whether it's hydronium or hydroxide, it can interfere with different things. It's going to become more and more reactive, I should say. The more the smaller the pH or the greater the pH, it becomes more and more. Let's analyze a little bit here about rain. Rain has a pH of 5.5, but if you get below 5.5, we call it acid rain because it's becoming more acidic. And acid rain is very, very harmful to plants because plants do not have any type of organs that can filter out this higher acidity. We can drink things like lemon juice and wine because we have our liver, we have kidneys. We can take things out of our blood that don't that we need to take out of our blood. Let's put it that way. We can take things out of our blood because we have those organs, but plants don't. So plants have to take whatever they pull out from the roots, and if it is hazardous to them, they can't filter it out, and it kills them. So that is what you know, we have this line here at 5.5. Below that, we call it acid rain. So if you have an area with acid rain, you want to keep your plants alive, what can you do? Well, you could put things that acid rain would react with, or acids would react with, which would be bases, to protect your stuff. So, or it doesn't have to necessarily be bases, but like you could put like carbonate, things with carbonate in it, like chalk or eggshells or something like that, and then the acid would start reacting with the carbonate. You could put that right on top of the soil, reacts with the carbonate, and it doesn't go into the soil, so it doesn't let the soil get as acidic. So you can do things to treat that acid rain. I believe that was an old AP environmental science test question. You know, they asked what could you do to deal with acid rain, and that would be some examples. The chemistry falls into all kinds of different categories here. Okay, this workshop has two parts. The first part here is there's one question, and it's to classify the following substances as acidic, basic, or neutral. So I've got some different things here, and just a quick little refresher. There's two slides to this one. So the first one here is soap, and I'd already telling you that the soap solution has a pH of 9. Look at that. Sour liquids. If we think about that, lemons were acidic, oranges are acidic, so things that are sour are acidic. So sour liquids, that's below 7, and the key thing here is this is above 7. How about C? A solution with 4 times as many hydronium ions as hydroxide ions. When you answer this one here, you should go back in your notes and take a look at what is the definition of hydronium and what's the definition of hydroxide. Are we talking about acids or bases? And I have 4 times as many of this one, so you should be able to figure out if that's an acid or a base. And D, with pure water, you got equal concentration of hydronium ions and hydroxide ions. If you have equal amounts, would it be an acid or base? Hint, that's a trick question. All right, the next questions, number 2. Arrange the following substances in order of increasing acidity. We've got vinegar, gastric juices, stomach acid, and soft drink. So we've got these values here. Put them in order of increasing acidity. So remember, is it getting more acidic if the number is going greater, or is it getting more acidic when the number is going smaller? So put those in order based off of acidity. Number 3, a solution with a pH of 2 is blank times more acidic than a pH of 6. Remember what I talked about here when you're talking about magnitudes of 10. Do you put a number in front? Do you put zeros behind? And the same thing goes with number 4. How many times more? Number 4 is just like 3. How many more times acidic are the following comparisons? So we've got these guys here, and when you do these ones here again, and just like number 3, if there's a difference of 2, that would mean you would add 2 zeros. So this one here would be 100 times more acidic. By the way, this one here would be a magnitude of 4, so that a pH change of 4. So that would mean that you'd have one with 4 zeros, which would be 10,000 times more acidic. I think you can figure out the rest on your own. Save those questions for me, and I will talk to you later. Ciao.